Section 10.1, Systems of Linear Equations in Two Variables, Part 1. A system of equations is a set of equations that involve the same variables. And here's an example that we're looking at. We have a set of equations, two of them, and each involve the same variables x and y. The set of equations is linear. Linear, if I look at the variables, they all have a power of 1. So they are a linear set of equations. Since it's a linear equation, when we graph, we're going to get the graph of a line. A graph of a line for the first equation, a graph of a line for the second equation. A solution of the system is an ordered set of numbers such that each equation is satisfied if there exists that ordered pair. And here in this example, this would be considered our ordered pair. The variables involved were x, y, so in this case x is 4, y is 1. If I were to plug 4, 1 into the first equation, I'd get a true statement. Plugging 4, 1 into the second equation, we get a true statement, so that would be a solution of the system. Now, since we are graphing two lines, there's a graphical interpretation for solving this system. Here, when I look at types of solutions that we can end up with, we can end up with exactly one solution, meaning that our graph, if we were to graph the two lines, they intersected once. If we graph the two lines, they don't intersect at all, so that would be a no solution. If I graphed the first line and then I went to graph the second line, it fell right on top of the first line, then we would have an infinite solution. So when we solve, we're either going to get one solution, as in the case of our example for 1. We could have no solution, or we could have infinite solution, and we'll be looking at all three data types. Okay, we can classify systems in one of these three ways. If a system is independent, what that means is when I graph the two lines, they were two separate, two distinct lines. So those systems would be independent. If we were to graph and they're the same line, then the system is dependent. They're the same graph, so the system is dependent. Okay, consistent means that there's a solution, either one solution or many solutions. Consistent, you have a solution. Inconsistent would then mean there is no solution. Okay, let's look at some examples. The first method that we're looking at solving for is substitution. We choose one equation and solve for one of the variables, and then substitute that into the other equation to get an ordered pair if one exists. Okay, the example that we see here, we can easily solve equation 2 for x. We can easily solve equation 1 for y. So these would be two variables that would be easily to solve for. And that's what we're looking for. We want to solve for one of the variables. It doesn't matter which equation we choose. We can solve for x in equation 2. We can solve for y in equation 1. It doesn't matter. We just choose one equation and solve for one of the variables. Let's say we decide to solve for x. So to solve for x, we would subtract over to the 2y. Now we're going to substitute this expression into the other equation. So we're going to take this and substitute it in for x. So that would leave us with 2. X is 2 minus 2y plus y equals 7. So that would be 4 minus 4y plus y equals 7. So we would have 4 minus 3y is equal to 7. If we subtract over that 4, 7 minus 4 would give us 3, and y would be negative 1. Okay, so far in our ordered pair, we know y is equal to 1. If y is equal to 1, how can we figure out what x is? We can take that equation, 2 minus 2y. We'll substitute in a negative 1 for y. So we get 2 plus 2, which is equal to 4. And there's our remaining, or our missing piece. There's the ordered pair that satisfies both of these equations at the same time. The methods for solving are substitution, which we just saw. Now we're going to do an example for elimination, and then we'll move on to the graphical method. Okay, in elimination, we multiply one or more of equations by an appropriate number so that the coefficients are the same, one negative, one positive. Then we add the two equations together, eliminating a variable. Looking at problem number 12, it would be nice if instead of 2, we had 6x, and in equation 2, if we had a negative 6x, if I were to add these together, we would eliminate x. Okay, that's elimination method. Let's see how we can make this position a 6x. We can make it a 6x if I multiplied everything by 3. So that would be 6x minus 15y is equal to a negative 18 times 3 is 54. Okay, how can I make this a negative 6 if I multiplied this by negative 2? So I'd get a negative 6x minus 8y is equal to 19 times negative 2 is a negative 38. Adding these together, we've eliminated x. Negative 15 minus 8 is a negative 23. Negative 54 minus 38 is a negative 92. And if I take negative 92 and divide by negative 23, we get y is 4. So our ordered pair, so far we know y is equal to 4. Okay, so let's try to find x. It doesn't matter which equation we choose. It doesn't matter. You can choose either one. I'm going to choose the second one just out of randomness. We have 3x plus 4y, which we say is positive 4, is equal to 19. So we're just going to substitute in our y is equal to 4. So that would give us 3x plus 16 is equal to 19. 19 minus 16 would give us 3, and so x is equal to 1. And there's our ordered pair, an xy value that satisfies both equations at the same time. Okay, so we saw substitution, we saw elimination. Now let's look at the graphical method. Okay, for the graphical method, we're going to solve each equation by graphing in the same viewing window. For the graphical method, the solution is where they intersect if they intersect. Okay, so to get this in our graphing calculator, we have to have y solved for. So let's go ahead and subtract 2x. Let's divide by 6. So we have negative 2/6 over x, which reduces to a negative 1/3. We have negative 3x minus 9y equals 18. Negative 9y equals 18 plus 3x. Divide everything by negative 9, and we get y is equal to, this is going to reduce to a negative 1/3 x, and this is going to reduce to a negative 2. We're going to put this in y1, we're going to put this in y2, and we're going to look for an intersection point if there is an intersection point. Okay, so I've already put these in, y1, y2. We're going to do a zoom standard. Let's look for an intersection point. We see that these lines are parallel. They have the same slope. Since the lines are parallel, where are they going to intersect? They're not going to intersect at all, and so we would have infinite solutions.